Welcome, everyone. This is the last talk this year, and really happy to have Flavio from Harvard. And he's going to talk on representations and fairness, information-theoretic tools for machine learning.
Cool. Well, thank you so much for inviting me. I guess this is a part where I share my screen.
Yes.
Yes, yes.
Okay, cool. Let me share and let me see if this works. Cool. Can you see the slides? Great. So thank you so much, Salim, for inviting me. I'm excited to be here today to talk about some of the work that my group at Harvard has been developing on representations and fairness, a few information-theoretic tools for machine learning. One of the great things of being faculty is that you get to travel and give talks, and I guess give talks that are streamed about the work that was done by an amazing group of students. So a lot of the results that you're going to see today were the fruit of the effort of a great batch of students at Harvard and postdocs and elsewhere, Sean and Hao, who are my PhD students, Weil, who is a PhD student as well, Madeline, who is also a PhD student here at Harvard, Burke, who is a postdoc at Circus, and Salman, who's a graduate student at MIT. So I'm going to start my talk with a quote that I heard many times while I was working at IBM a few years back, which is a quote from the CEO of the company, Jenny Rometty, where she states that, "I want you to think about data as the next natural resource." And if you think about other natural resources, things like oil, natural gas, uranium, and so on, what you realize is that data, just like these resources, is collected and processed by companies in order to provide useful services. But like these other resources, they can be misused and must be handled with care. So with the massive collection of data that we see today, the massive collection and processing of data by companies like IBM, Amazon, Facebook, and so on, you get all these useful services like online advertising, like search, like social networking, and so on. But with big data also comes big responsibility and exciting new challenges and important new challenges in areas such as privacy, fairness, and transparency, trying to understand how these algorithms work and why they may be making some decisions that you're observing. And this talk starts from the premise that information theory can help us understand privacy, fairness, and transparency in machine learning. And specifically, a fundamental perspective, an information-theoretic perspective, can help us understand some fundamental challenges in these different areas. And what I'll do today is that I'll be introducing a few information-theoretic tools that are useful for tackling problems in fairness, privacy, and representation learning. And specifically, I'll be focusing on one tool that we're going to be using today, something that I like to call the principal inertia components, but it's also something that has appeared with many different names out there in the literature. So today I won't have a lot of time to talk about privacy. I'm trying to keep this talk within 1 hour, but I will be talking about how these tools are useful in fairness and also to help understand representations made by complicated machine learning models. But before I get there, I just want to give you a bit more motivation about why these problems are important and also give you a brief outline of the talk. So I'm going to start giving a bit more motivation about fairness, privacy, and representation learning and kind of introducing the setting that we're going to be addressing today. Then I'm going to introduce the main character of our show, which is the principal inertia components. You can think about that as the fine-grained decomposition of the dependence between two random variables, then apply them to one aspect of representation learning, one aspect of fairness, and if I have time, talk a little bit more about some of the work that my group has been developing. So let's start with a bit more motivation and talk about fairness and also the specific setting that we're going to be considering in representation learning. So machine learning algorithms are increasingly used in applications of individual level consequence. These are applications that can literally change someone's life, something like recidivism prediction, criminal justice, and personal finance, also employment decisions and hiring, things like companies like ZipRecruiter do. A natural question to ask in these settings is, do these algorithms discriminate on race, gender, or some other protected attribute? So why do we care about this question? Well, hopefully we care about this question not only because all of us want to live in a more fair and equitable society, but also because it's the law. So if you're at Rutgers, for example, listening to this talk, and tomorrow you make your great new machine learning startup, that uses analytics for job hiring, for example, there's very clear regulations of what may constitute discrimination. And just to be clear, whenever I say discrimination in this talk, I don't mean discrimination in its usual Bayesian sense. I mean discrimination in its social sense. So discrimination as the prejudicial treatment of an individual based on membership in a protected group. So it turns out that machine learning algorithms can discriminate. One example is something that Google changed recently, actually. This screen grab is from a few months back. But until recently, if you went to Google Translate and typed in "she is a doctor, he is a nurse," and translated to Turkish, Turkish is a gender-neutral language. It doesn't have gender pronouns. And get the translation and translate it back, you will get "he is a doctor, she is a nurse." The he and the she is flipped, right? Why does this happen? Well, this happens probably because the algorithm that is behind Google Translate was trained on data that was biased, right? And now it's just propagating this bias in its output translations. And this bias propagation is specifically concerning in other applications, such as criminal justice, right? There are studies that have shown that recidivism prediction instruments used in different counties in the United States can have different levels of accuracy and produce different marginal decisions conditioned on your race. The discrimination by machine learning algorithms have appeared in many other applications such as facial recognition. The New York Times had recently this article with this great title, "Facial Recognition is Accurate If You're a White Guy," based on the work that was done by a student here at MIT, actually, where she demonstrated that commercially available facial recognition software had higher error rates for African-American females, for example, than for Caucasian males in a gender recognition task. And this has appeared in many other applications in natural language processing and so on. So why do we observe this discriminatory behavior? So the bias in machine learning algorithms can stem from many different sources. And today I'm going to be focusing on one specific setting that I'm going to motivate next. So one potential source for this bias is what is known as disparate treatment. So assume that you have a machine learning model represented by this box here. It's a classifier. And this model might, let's say that this model is doing recidivism prediction, predicting if someone will commit a crime again in the near future or not. This model receives legitimate inputs X, what we call decision variables. For example, the age, the criminal history of the individuals that you're using the data to predict an outcome Y hat. For example, will this person commit a crime again in the near future or not? So if you use a sensitive or protected attribute S directly as an input to the model, you have what is known as disparate treatment, right? Because the decisions made by your model may depend directly on this sensitive attribute. More pervasive nowadays is what is known as disparate impact, where you don't use these sensitive attributes directly, but you use variables that are proxies for this attribute as an input for your model. Just to be a little bit more precise about the setting that we're going to be considering, you can think about this as conditioned on this sensitive attribute. Let's say your binary variable S is 0 or 1. Conditioned on S, the distribution of input features changes. And this might induce a difference in performance of your model, right? And this difference of performance, I'll have a lot more to say about how we capture this. There are different metrics that are used in the fair machine learning literature, but usually it's given by some kind of average performance difference condition on these different groups. For example, a different level of accuracy condition on S equals 0 or S equals 1, maybe the different percentage of outcomes that you're marking as recidivists. And I'll have more to say about that later. And in this talk, when we talk about disparate impact and disparate treatment, our goal will be to repair a classifier that has disparate impact by pre-processing the data, asking how would we change the data in order to remove some kind of difference in performance that we're observing. And in this case, I think it's not just the destination that matters, but the journey is important as well, because along the way, we're going to be developing a few tools that will help us understand how these differences in distributions lead to a difference in performance of your model. So this is what we're going to be analyzing when we talk about fairness in machine learning. We're going to be using very similar tools, essentially tools based on these principal inertia components, to tackle the problem of representation learning. And specifically, we're going to be using the PICs, these principal inertia components, to understand how to produce maximally correlated representations of data. And our goal will be to reason about representations learned by complicated machine learning models. And we're going to be reasoning about these representations, for example, the intermediate layers of a neural network, as points in the Hilbert space of finite variance functions. And that will allow us to do one kind of statistical analysis known as correspondence analysis at a very large scale. So to summarize, this is what's happening next in this talk. I'm going to introduce a few information-theoretic tools that are useful in representation learning and in fairness. And the main workhorse, and I think that's one of the beautiful things about information theory, is that we can use basically a common set of theoretical ideas, in this case, principal inertial components, to tackle these two different problems. Okay? Great. So what I'm going to do next is that I'm going to introduce the main star of our show, which will be the main tool that we're going to be using, known as the principal inertial components. And you can think about these information-theoretic creatures as a fine-grained decomposition of the dependence between two random variables. So we're going to step away from applications for a little bit and just look at the introduction. And I'm just going to introduce and describe a bit more about these PICs. So what I'm going to do next is that I'm going to give you two equivalent definitions of the same thing. So these are two ways of defining these information-theoretic quantities called the principal inertial components. So the first way of defining them is in terms of maximizing correlation. So let's assume that we want to play a game. I have a random variable X and you have a random variable Y. And these variables are, they could be distributed over apples and oranges. It could be an image and a caption. I don't know. They're two dependent random variables, X and Y. And our goal is to find two functions. I'm going to find a function of X. You're going to find a function of Y that maximizes the correlation between f of X and g of Y. And to avoid trivial results, we're going to restrict these functions to have zero mean and unit second moment. This is what this norm notation means, like unit variance. So if you were to solve this problem, the solution for this optimization is what is known as the maximal correlation between X and Y. And it's given by the square root of the largest principal inertia component. So let's say we solve this problem. We find these maximizing functions. We're going to call them F1 and G1. And let's solve the problem again. So now we're going to solve the same problem, but we're going to search for new functions. I'm going to search for a function f of X. You're going to search for a function g of Y. That also maximizes correlation, but now they're uncorrelated or orthogonal to the previous function f1 and g1 that we found. So if you were to solve this, you will get the second principal inertial component, the square root of the second principal inertial component. Let's say the solution of this is f2 and g2. You add it as a constraint again, solve the optimization. You get the third principal inertial component, and so forth. So these sequence of functions that arise are what we're going to call the principal functions. And the solution to this optimization is what we call the principal inertia components. And they will be very useful to try to reason about representations learned by complicated machine learning models. We're going to be looking at that next. So that's the first definition that I wanted to give you. I'm going to give you a second entirely equivalent definition for the same quantity, which is what is the spectrum of the conditional expectation operator. Those of you who are more familiar with linear algebra, this previous procedure that we did looked a lot like a singular value decomposition. And it's exactly what that we were doing. Like the second question is, what is the spectrum of the conditional expectation operator? The conditional expectation operator is a linear operator that maps the space of finite variance functions of a variable y to the finite variance functions of variable x, given by conditional expectation defined in the middle of the slide. And if you were to diagonalize this operator and look at the singular values, the square of the singular values are exactly the principal inertial components. And this will be useful for us in fairness, because this interpretation will help us understand local perturbations of measures and how that influences the decision made by a biased machine learning model. So why should we care? Why are these quantities interesting? Well, this is a formula that a lot of people haven't seen before, is that if you give me a joint distribution between X and Y, for example, here I'm using lowercase, assume that just for now that everything is nice and discrete and over a finite alphabet, you can decompose this joint distribution as P of X times P of Y. So if you didn't have this term in parentheses, you would have an independent distribution. And what gives this coupling between X and Y is the term within the parentheses, right? Which is exactly 1 plus the PICs times the principal functions. Okay, so you can think about this like from a very loose, intuitively from a high level, and loosely speaking, as a fine-grained decomposition of the dependence between X and Y. So how would you compute these principal inertial components? Well, one way of computing them, and this is actually something that's done in the correspondence analysis literature, is by taking the singular value decomposition of this matrix. So if everything is nice, discrete, and finite, one way of computing the principal inertial components is building this matrix, the matrix where the entries are the joint distribution divided by the square root of the product of the marginals. And if you were to take the SVD of this matrix, the singular values correspond to the principal components, and the left and right singular vectors would correspond to the principal functions. Okay, so if everything is discrete, this is how you would find these quantities. And the principal inertial components is something that definitely wasn't introduced by me. This is something that has a very long history in the mathematics, probability, and information theory literature. They date all the way back to the work of Hirschfeld, Gebeline, Sarmanov, and Reyni in the context.
I have a question. Sorry to interrupt. So in the previous results, so are you saying like if the variables are discrete, then these principal components are linear functions?
No, they're not linear functions.
They're not.
No, these functions are usually highly nonlinear.
Oh, okay.
Yeah. But if everything is discrete, the function can be represented as a vector as well.
Okay.
And they will correspond to this left and right singular vectors.
Okay. Sorry.
Okay. Great. So as I was saying, this is something, these quantities, they have a long history. They've been studied in the context of maximizing correlation. Information theorists have studied them in the context of contraction coefficients and strong data processing inequalities. Work by Witzenhausen, for example, also some very exciting work done by Li Zhongzheng, Greg Varnell, Xiaolong Huang, and Anuran Makur at MIT. And they've been studied from the statistics perspective in terms of decomposing contingency tables. There are other methods that seek to estimate these principal inertial components, such as the alternating conditional expectations, ACE algorithm. And if you want to see a more detailed overview of this different literature, you can check out one of our papers, Principal Inertial Components and Applications in the Transactions of Information Theory. And what we're going to bring to this table today is that we're going to apply this PICs to understand local perturbations in fairness and also to study data representations learned by complicated machine learning models. And specifically, these two theoretical interpretations that I gave, the thinking and viewing the PICs in terms of maximizing correlation, we'll be using that for reasoning about representations from machine learning models. And this intuition as the spectrum of the conditional expectation operator we're going to apply that to fairness and to understand perturbations of probability distributions. So these are the two facets that we're using. I'm gonna now go over the first application that where we can use the PICs to reason about machine learning models and use this interpretation of maximizing correlation. And specifically, what I'm going to do is that I'm going to use the PICs to perform one kind of statistical analysis called correspondence analysis at a very large scale. So as I mentioned, one way of estimating these principal functions and the principal inertial components is by building this matrix Q here. And if you give me a collection of data points over a discrete alphabet, I can estimate this matrix. I can just normalize a contingency table, which is a matrix with the relative frequency of each symbol that I observe, and take its singular value decomposition and try to estimate the PICs. The limitation of this approach is that first, it requires categorical data, and second, it doesn't really scale for very large alphabets, right? If you can assume that if your alphabet is very, very large, estimating this matrix is challenging. And there are some other methods, such as the alternating conditional expectation algorithm, that might run into similar issues. Nevertheless, this problem of estimating this matrix and estimating the PICs is central to correspondence analysis. So correspondence analysis is, you can think about this as a nonlinear CCA, canonical correlation analysis, if that means anything to you. And it's a statistical method that appears in several papers in epidemiology, psychology, chemistry. There are books written about that. And what correspondence analysis tries to do is that it tries to do, as I mentioned, something that looks like a nonlinear CCA. So if you give me a data set of two random variables, X and Y, drawn IID from some joint distribution P of XY, this is what I would do with, this is how correspondence analysis works. I would build that matrix. I would estimate the principal functions, right? And then for my variables X, I would create this orthogonal plane where I plot on the X-axis the first principal function, on the Y-axis the second principal function. So here, each point is a sample, and these are the principal functions that you would find by decomposing your matrix. You would do the same thing for your random variables Y, right? You would jointly plot the first principal function for Y and the second principal function for Y, and you would try to find correspondences, right? You would try to find correspondences between outcomes of X and outcomes of Y. And why does this make sense? Well, this makes sense because of this decomposition formula, right? You would assume that the points that are close to the middle, these are points that have low correspondence, right? Where the joint distribution between X and Y are close to the product of the marginals. The points are close to the origin. And the points that are very far apart, we potentially have high correspondence, right? We can find a nonlinear transformation of the data so that these variables are highly correlated. So this is how correspondence analysis works, right? But as I mentioned, as it's usually done by decomposing a contingency table, it doesn't really scale to high dimensional data. So in order to scale up correspondence analysis, and we're going to try to use neural networks for that, we need to go back to theory, right? And to the information-theoretic interpretation behind this method. So as I mentioned earlier in the talk, you can think about maximizing correlation as computing the PICs in terms of maximizing correlation, right? So we could either build that very large contingency table, that very large matrix, try to estimate it and decompose it, or we can try to solve this optimization problem where we find functions f and g that are maximally correlated and have zero mean and unit variance. Well, this problem is still not something that scales. It's something that requires you to search over the space of all possible functions of your variable X and variable Y. But as long as we can search over a large enough space of functions and have enough samples from X and Y, we might be able to recover these PICs. And luckily, over the past few years, we've developed very, very fast methods for searching over a large space of functions. And the way we do that is using neural networks. Right. When I think about a neural network, when I think about the output of a neuron, maybe at the output or maybe at the intermediate layer of a neural network, I think about this neuron as a point, right, in the space of finite variance functions of your input distribution. Right. And I think it's reasonable to assume that these functions have finite variance, unless you're usually you have something like a sigmoid or a tanh, or even if you have a ReLU, but then it will have most likely finite variance. And in this case, each one of these neurons forms a point in this Hilbert space of finite variance functions. And then we can start talking about basis of the basis composed about from these functions, or other functions do they span, and so on. But what we will do is that we're going to use these neural networks as a vessel for searching over this large function space in order to estimate the principal functions. So if you give me a neural network that searches over functions of X and give me a neural network that searches over functions of Y, as long as I can cleverly design a loss function that corresponds to maximizing correlation, I can backpropagate on this loss and try to find maximally correlated functions. And this is exactly what we do. The loss function is here. This appeared in a recent an AI stats paper that was presented earlier this year. I'm not going to go through the details of how this loss function is derived. You can think about this as estimating correlation over mini batches of your data. This is what we're doing. A similar loss function has appeared also in a paper called Deep Canonical Correlation Analysis by Andrew et al., even though they don't make this connection to correspondence analysis. So great. So this is how we are going to estimate the PICs. Let's see how this works in practice. So as a starting example, let's see if we can overcome one of the challenges that we had in the contingency table approach, which is estimating the principal functions for continuous random variables as opposed to discrete random variables. So here's one example where an X and Y are jointly Gaussian. So what we're doing is that we're generating X and Y from a jointly Gaussian distribution, feeding samples of X to one neural network, Y to another neural network, and trying to estimate these principal functions. In this case, we know what the principal functions are. They're the Hermite polynomials, or neighborhood friends. They're polynomials that are orthogonal under the Gaussian measure. And you can see that the neural network actually does a good job in estimating these functions, right? So as you, for example, if you have 5 outputs, the first function will correspond to a constant, the second function is a linear function, the second function will be a quadratic function, and so forth. And of course, your approximation becomes worse and worse and worse as you go to higher order polynomials because your PICs decrease. So this is encouraging because this shows that at least in certain theoretical settings, we can recover the principal functions that are predicted by theory. And now what I'm going to show is how we can perform correspondence analysis using this training procedure. So again, we have samples from X, we have samples from Y. We're gonna feed it to 2 neural networks and fit the neural networks according to this loss function that aims to maximize correlation between f of X and g of Y. And we're gonna use this to do correspondence analysis. So again, for the samples X, once we find these functions, we're gonna feed it through the neural network, and we're going to plot in the X-axis the first function and the second axis the second function. Same thing for the functions that we fit for Y, and try to understand correspondences between X and Y. And by using these neural networks, we can perform correspondence analysis at a scale that, as far as I know, hasn't been performed before. So this is one example. This is on the Kaggle food competition dataset. This is here X corresponds to ingredients that compose a certain recipe. So we're feeding to one neural network a vector of ingredients that compose a recipe, and Y corresponds to cuisines. And we're doing this training procedure and trying to find correlations, right? Maximal correlations and correspondences between our ingredients and our recipes and our cuisines. So the squares in this plot correspond to the different cuisines, and each dot here is a recipe. There are like a few tens of thousands of recipes in this plot. And what's interesting is that you can see that the neural network learns to extract these correspondences. On the right-hand side of the graph, you see a lot of the Asian cuisines clustered together. On the top left-hand side of the graph, you see the European cuisines clustered together. And this purple square right in the middle of anything, I don't know if you can read what it is, but that's a Brazilian cuisine. Yeah, I'm Brazilian. I grew up in Brazil, and I was excited to see this. It's like right in the middle of everything, at least in terms of these first 2 principal functions. And if you were to compare the amount of correlation that we can extract between the transformed samples, it's much higher. This is on the test set than if you were to build this contingency table and do an SVD, or even if you were to use a canonical correlation analysis or a kernel KCC, a kernel canonical correlation analysis. We've done this with other data sets. This is another example with the UCI wine quality data set. In this case, X is about 5,000 red wines described in terms of 11 physiochemical attributes. Most of them are continuous, and Y is discrete. So we have 6 levels of quality. And you can also find here in the first plot, the first and second principal function for where we cluster together wine properties in terms of their quality. It's interesting that if you interpolate between a bad wine and a good wine, you can see that it going from the blue dots to the brown dots, you can actually see that it goes in between the medium wines. So it does this nice nonlinear interpolation. In this case, we only managed to capture 2 principal functions. You can look at the third direction of variation, and it captures very little correlation. Another place we've applied this is to try to understand how Brazilian congressmen spend their discretionary funds. Like, this is based on the analysis of a very massive data set where we have about 9 million reimbursement requests from congressmen in Brazil, where they request a certain amount of reimbursement for different expense categories that they can declare. This is all based on open data. In this case, X is a Congress member and their party. Y is the expense category and the value. And we ran this to try to identify outlier expenses and try to correlate it as well with the number of investigations that are open against each congressman. And you can clearly see directions where you have outlying expenditures that are highly correlated with the party or the congressman. For example, in one area, which is disclosure and advertisement of parliamentary activity, which has been noted to be an expense category where money is misused. And since I'm being live streamed, that's all I'm going to say about that. So you can ask me more about this analysis offline. And we've also scaled this up to many other data sets for if you're doing just to show that it scales and things that involve images, Cypher 10, Cypher 100, and so on. And if you want to learn more about the work that we did on this, please check out our correspondence analysis using neural networks paper, last AI stats, and we have a more polished and extended version on an archive called correlated embeddings of pairs of dependent random variables. So this was the first part. So for the rest of the talk, we're going to switch gears a little bit and look at the second application of these principal inertia components, which is to understand how to repair models that might present bias in machine learning. And specifically, we're going to be looking at the interpretation of the PICs as the spectrum of the conditional operator, and in terms of local perturbations of probability distributions. Okay, so we're still going to be using the same set of ideas, but we're shifting gears a little bit to a different application. This is the setting that I introduced a little bit earlier in the talk, and I'm just going to refresh your memory of the setup that we're looking at, which is this disparate impact setup in machine learning. So in this case, we have a model represented by this box. This model receives a certain set of input variables X and produces an outcome Y hat, right? This outcome Y hat tries to approximate a true outcome Y given by this green box. This green box is something that we can't control. It's something given by nature, some phenomena that we observe by society, but it's not something that we can actually intervene. This is what we're trying to approximate via a model. And we also have a set of sensitive attributes S, and conditioned on S, the input distribution of variables to our model changes, and this may lead to a difference in performance of our machine learning model. And the question that we're going to be asking for the rest of this talk is the following. How does the performance of the machine learning change when I change the input distribution of the data? Specifically, if I have a population that has a more unfavorable performance, how does small changes in this input distribution lead to a variation of performance in the model? Why are we asking this question? Because perturbing the input distribution will enable us to first compute influence functions for fairness metrics. Second, try to identify potential proxy samples and features for discriminations. Try to identify features that might be proxies for your sensitive attribute. And it will allow us to propose at least one method to repair bias in the classifiers by pre-processing the inputs. And this is based on a paper that we just presented in this year's ICML. And if we know a new distribution of the data, we will give one method of pre-processing the data, changing the data from one group before feeding it to the classifier in order to mitigate this disparity. And the way that we're going to build this preprocessor is in 2 steps. The first step is to identify something that we call the counterfactual distribution. So counterfactual is a very loaded term. I'm going to give the very specific meaning. I'm going to define exactly what we mean by counterfactual here in a few slides, which is this hypothetical distribution that would minimize disparate impact. And if we have a target distribution that removes this bias, we can solve an optimal transport problem that maps samples from my original distribution to the new distribution. And this is how we're going to design this preprocessor. There are many preprocessing methods out there. There are many fairness intervention methods for trying to correct the model for bias that's appeared over the past few years. This is a extremely incomplete list. But again, what I think is interesting in our approach is not just a method for repairing bias, but also this mindset of thinking of perturbing distributions in order to understand where this bias may be coming from. In order to do that, we're going to make 3 assumptions. So for this section of the talk, I'm going to make 3 assumptions of things that we have in hand. The first thing is the model that we're going to analyze in order to correct for bias. So we're going to assume that this is a black box model. I don't care if it's a neural network. I don't care if it's a logistic regression or a random forest. I don't know what it is. I'm not particularly interested in the details of this classifier. You can think about this as an API that or something that runs in the cloud where I just send samples and get predictions back. But I'm going to assume that this black box model outputs something that looks like soft decisions. So a probability distribution over the set of possible outputs, something like a logistic regression. I'm going to assume that I have an auditing data set. So this data set is a data set that I collected from the population over which this model is deployed. If I don't have such a data set, it's even questionable how I would check this model for bias. And I'm going to assume, just for the sake of these slides, even though our paper encompasses a more general setting, that my sensitive attribute is binary, and that the true outcome that I'm trying to predict is also binary as well. So the third thing that I'm going to assume that I have is a fairness metric, right? And there are many. I'm not in the business of proposing fairness metrics, even though business is booming. But what we will be looking at is at what are so-called group fairness metrics, right? So we're going to try to make this approach as general as possible so that you can instantiate for some of the many different metrics that have appeared out there. So we're going to be focusing, as I mentioned, on group fairness metrics. These group fairness metrics are usually defined in terms of differences between average outcomes and error rates across populations. And maybe if you're a grad student and you're listening to this and you're interested in fairness, what I'm going to give you next is just a general recipe of how you build these group fairness metrics. So a lot of the metrics out there, what you would do is that, again, assuming that you have two populations, you would, and assuming that your predicted variable is binary, you would build a confusion matrix for the first population with a true negative, false positive, and true positive rate. You would build another contingency table for the second population, and you're going to compare the entries of this table, right? And depending how you assume the entry, how you impose equality, or that these entries are similar, you have different notions of fairness, of group fairness that have appeared in the literature. So one example is that you may want to ensure that the marginal distribution of the output of your classifier is close for each group, right? This is known as statistical parity. You can think about your model being something that approves loans, and you want the fraction of loans approved to the first population to be close to the fraction of loans approved to the second population, or to population 0, be close to the one approved to population 1. Maybe you want to have similarity in false positive and true positive rates. This is another notion known as equalized odds, where condition on the true outcome, you want the probability that you mark the output of your model y hat is equal to 1 to be close for both populations. If you only fix the true positive rates to be similar, this is known as equal opportunity. But as you can already observe, there are combinatorially many metrics that you can define from this table, and there's several papers out there that have been studying trade-offs between these metrics and so on. So we're not as interested in one specific metric. We're interested in group fairness metrics in general. So we're going to be considering the metrics that are described in this table here. So for example, what I'm going to describe next would apply to something to statistical parity, to false discovery rates, equalizing false negative rate, false positive rates, or any linear combination between these metrics. We can also do that. But we will make the following assumption. We're going to assume that we have what we call a target group. We're going to just mark this as S equals 0. For example, this is a group, maybe a minority group, where you observed that your model has a least favorable performance according to some of these metrics. And we're going to assume that that green box, the channel given by nature, and that the distribution of features over the baseline group, the one for which we want to equalize the performance, denoted by S equals 1, and that this fraction between both groups are fixed. So if you assume that the marginal distribution of the true outcome P of Y given X and S, the distribution of input features for the baseline group, and the prior P of S is fixed, then all of these metrics in this table, they can be cast in terms of the distribution over your target group, the group that has unfavorable performance. That's the only thing that matters. And given that these conditions, we're going to do the following thought experiment. This is a hypothetical question. It's not something that we can actually go and do in practice, but we're going to ask, can we find a new distribution over the target group that minimizes a given disparity metric? All other things fixed. If you give me a disparity metric, how would I change the distribution over the target group in order to minimize disparity? So
can you explain more what are the parameters here? How can you change the distribution on the target group? What does it mean exactly?
Yeah, so we can't actually change it.
Oh, okay.
Yeah, so that's my point. It's not something that we can actually go and change, but we're just gonna go through this thought experiment.
Okay.
Yeah, and just a sneak preview of what's going to happen later is that these, we're not actually going to compute a new distribution. This will give us a set of resampling weights, so that the resampled data set will mimic one that came from a new distribution.
I have another question, maybe too simple, but why not have two classifiers for each group?
Yeah, you could have that as well.
But and then you don't have a fairness problem, right?
Well, there are certain applications where you can't necessarily train two classifiers, and other applications you can. This is actually a debate to be had. Like, well, maybe if you train two separate classifiers, you can have a more accurate prediction for both groups. But then if it's something like loan approval, like there might be issues if you use certain sensitive attributes directly as an input to your classification algorithm. In other applications such as medicine, maybe that's not such a big deal. So yeah.
It's like having two set of laws under the same, it's like, yeah. I mean, it's even unfair to decide. You may be unfair by deciding which classifier to use, maybe.
Yeah.
Okay, thanks.
Okay, so we're going to ask this hypothetical question. In this case, you can, I'm going to illustrate what we're going to do through a cartoon. So what this blue triangle represents is the probability simplex. So it's a set of all possible distributions over input features. So the distribution over the target group will be a point in the simplex. The distribution over the baseline group will be another point on the simplex. And if you were to sample from, for example, the distribution P of X given S equals 0 and feed it to the classifier, that would induce a distribution over outputs denoted by this P of Y hat given S equals 0 and P of Y hat given S equals 1. And if you were to sample from one of these distributions and feed it to this true channel given that we're trying to approximate, you would induce also the true output, the true marginals P of Y given S equals 1 and P of Y given S equals 0. And what we're trying to do is that we're trying to find this new set of distributions. We're going to call them the counterfactual distributions, such that if the distribution over the target group were in this set, we wouldn't observe a difference in performance. So this gray set is what we call the counterfactual distributions. They're counterfactual because if my target group came from that distribution, we wouldn't observe the disparity according to a metric, right? And this is the formal definition here. We're trying to find a distribution Q of X that minimizes some disparity, where the disparity metrics that we're considering are given in this table or a linear combination of the ones in this table. So some of you may be thinking, well, why don't I just move my blue dot to the green dot? If I make both distributions exactly the same, then the output distributions will be the same. And this is not necessarily the case. The counterfactual distribution is not necessarily the distribution over the majority group, because that will be the case if you're considering statistical parity, where you want the marginal output of your classifier should be the same. But if you're thinking about false positive rates or false negative rates, because this channel that we're trying to model may depend on S. By making both distributions equal, you may actually be increasing the false positive or false negative rates over one of the over your target population. And what we're going to do next is that I'm going to give you just in pictures, like a way of finding this counterfactual distributions via a series of local perturbations of the measure P of X given S equals 0. And you can think about this as gradient descent in the probability space. And the interesting thing about this procedure is that it provides insight into potential proxies for discrimination. So again, if you're a graduate student or a student and you're listening to this, here's a neat trick. So how do you perturb distributions in the simplex without leaving the simplex? And usually you don't do an additive perturbation. The easiest way of doing this is via multiplicative perturbation, right? So I have my distribution over the target group, and I'm going to multiply it by this 1 plus epsilon f of x. And as long as f has 0 mean when measured according to P of x given s equals 0, and finite variance, I can make epsilon very, very large. And this is a perturbation that will not take me out of the simplex. And when you perturb things in this way, the output distribution also has a multiplicative form. It also will have the form P of y given s equals 0 times a multiplicative term where this function g is simply the conditional expectation of f given y. So just repeating what I just said, if you add a multiplicative perturbation to the input distribution, that induces a multiplicative distribution perturbation on the output distribution. And as long as epsilon is small, and this function comes from the space of all 0 mean and finite variance functions, the output perturbation is simply the conditional expectation of f given y. And what we saw earlier in the talk is that the spectrum of the conditional expectation operator is given by the PICs, and it fully characterizes these directions of perturbations over the simplex. Okay, so this is what we're going to be leveraging next. So what we're going to be doing is that we're going to be asking, how do we perturb the distribution over the target group in order to minimize, how do we locally perturb it in order to minimize this disparity? We're going to constrain it to these multiplicative distributions that have perturbations that have 0 mean and unit variance. Which direction should I choose? Well, we choose a direction that looks like something like a gradient in the probability space, right? We're choosing the function that will minimize this disparity. It looks like a derivative in the probability space. It turns out that when you formulate this problem like this, this local perturbation is directly connected to something that statisticians know and love, known as the influence functions, right? So, and here's a formal definition of an influence function, but informally speaking, you can think about having a very, very, very large data set, and you want to understand how the statistic that you're measuring over this data set changes when you perturb one of the samples, right? So that will be, how is it influenced by each one of your samples in your data set? And it turns out that both of these questions are connected. Characterizing the direction of steepest descent in this disparate impact measured according to one of these group fairness metrics is equivalent to computing a normalized version of the influence function for these different fairness metrics. And it turns out that we can derive a bunch of closed form expressions for the influence functions for the fairness metrics that I explained earlier. I'm definitely not going to go into the details of this. You can find the derivations in the paper. But every single one of these expressions, they depend on 3 key ingredients. So they depend on the black box classifier that we aim to audit. They depend on a classifier, well-calibrated classifier that approximates your marginal distribution belonging to the target group given X, and a classifier that approximates the true distribution for Y, given that you're a member of the marginal distribution for Y, given that you're a member of the target group. And if you give me these 3 well-calibrated functions, which is something that we could potentially estimate over the auditing data set, you can plug it into one of these formulas and compute these influence functions. So the influence functions in itself, they're very interesting because they allow us to identify things that look like proxies for discrimination, right? So if you give me a black box function, a black box model, I can, with my auditing data set, I can compute these influence functions. And these influence functions can be viewed as a proxy score for each one of these samples. in terms of, and they can be aggregated across features to find proxy scores for individual features. This is something that we've done. For example, this is one set of experiments in the adult data set where we find features that might correspond to proxies for a sensitive attribute, in this case, gender, in an income classification task. Great. So we know how to locally perturb the distribution. We know how to compute this direction via influence functions. So we can use this to try to find the counterfactual distribution. And the way you do it is something that looks like gradient descent, again, in the probability space. The way you do it is that you compute the influence function for your auditing data set. This will lead to a set of resampling weights given by the influence function. Then you resample the distribution through the perturbed data set from the weights. This will give you a new data set that mimics the perturbed distribution, that mimics one sampled from the perturbed distribution. And you just repeat this process again and again until you land on this counterfactual distribution set. And we have different experiments that show that this resampling procedure actually ends with a new data set that minimizes this discrimination gap. So as I mentioned, these influence functions in themselves, they're interesting, but you can also use them for model repair. And the way you do that is the following. If you, again, here's your classifier and you have samples from both populations. And you can design a preprocessor that changes the samples by solving an optimal transport problem. So you have a target distribution given by your counterfactual distribution. You have your original input distribution, and given a cost function that captures how much you're willing to distort each sample, you can solve this optimal transfer problem, and the coupling that you get is exactly the preprocessor that you can use to repair these samples. And we've tested this with different data sets as well. So for example, in the adult data set, which is a data set used in an income prediction task, or in the COMPASS data set, which is a criminal recidivism data set, where you can use to train models that predict criminal recidivism, can actually see that your baseline models without preprocessing has a performance gap in terms of the different metrics and different target sensitive attributes in the data. And after the preprocessor, this discrimination gap is removed, but at some loss of performance, right? So exactly characterizing what will be this optimal trade-off between removing this discrimination gap and minimizing your, for example, classification and still preserving your classification accuracy. That's still work in progress. So that covers that the applications of these local perturbations in the PICs in fairness. And just to wrap up, I want to quickly talk about some of the ongoing work that I've been doing with my group and also with collaborators. So as I mentioned, this is, we provided one method for preprocessing the data in order to remove discrimination. There are many other methods that do that. This is just one example based on another optimized preprocessing method that we proposed at NeurIPS a few years back, where on the x-axis, you have the measure of group fairness given by statistical parity. On the y-axis, you have accuracy of different classifiers in a task for predicting recidivism. So what we did here is that we got your COMPASS data set, trained a classifier to predict if someone will commit a crime again in the near future or not, and just analyze the performance of different classifiers. If you train a random forest, you have, using your sensitive attribute, in this case, race as an input, you have a huge difference in performance. If you don't use a sensitive attribute, in this case, S as an input, you have a slight decrease in disparate impact, but you also have a slight loss in accuracy. And these two dots are what we get by preprocessing the data. A natural question to ask is, what is the fundamental limit, right? What is the best trade-off that you can find between a given group fairness metric and a given target accuracy measure? And why is this an important question? Well, because this is how a lot of the fairness intervention mechanisms look like today. This is some figures that I borrowed from Sorel Friedler's and her team's paper called A Comparative Study on Fairness Enhancing Intervention in Machine Learning. This appeared this year's FatStar conference. It was a heroic effort where they compare many different fairness intervention mechanisms. And what you see here plotted is the performance of different methods that try to correct for bias, where on the x-axis you have a metric that looks like statistical parity. On the y-axis you have accuracy, and you have the performance of these mechanisms in different data sets. And you can see that they're all over the place, right? There's no method that Pareto dominates all of the others. So I think this is one place where information theorists can really help trying to understand what are the fundamental trade-offs that are involved when we're trying to correct the model for bias. We have recent results on that as well. This is a paper that's now on arXiv that was done together with collaborators from IBM, Dennis and Carthy, where we have one post-processing method that can be also used for pre-processing samples before you feed it to a classifier model to repair for bias. We think it has very good performance. From our experience, it performs favorably in comparison with many of the methods that are out there. It is based on information theoretic ideas, so make sure that you check that out. Another place that we're using this is also for privacy. So another work that it was just recently posted on arXiv as well is a method that we developed for obfuscating samples via information density estimation, where we try to estimate the information density between, say, different parts of a picture and an attribute that you want to hide. In this case, trying to estimate which part of the picture is correlated with your emotion, if you're smiling or not. And just by estimating this information density using a neural network, actually, you can kind of localize parts of an image, and that reveals a lot of information about your smile. In this case, it naturally locates your mouth. We repeated the same thing for and trying to identify words in tweets that reveal a lot about your political preference. And the idea here is that is to, again, use the ideas from information theory to try to identify or pinpoint potential privacy threats, even before we obfuscate them, right? Even before you disclose the data, you may want to identify potential privacy risks that may be incurred by releasing this data. Another problem that we're working on is also quantifying the impact of data set size and diversity on bias in machine learning algorithms. Just to give you a quick example of this, this is a screen grab I did a few months ago of wedding and Google image search. And what you see is a bunch of brides in white and grooms in suits. And of course, this doesn't necessarily correspond to our diverse notion of what a wedding is, right? So what does it mean to have a data set that's diverse enough in order to ensure that it has a favorable performance for different, let's say, sensitive groups? This is another question that we're tackling. If you're interested in fair machine learning, I do encourage you to look at the IBM AI 360 toolbox. It's a toolbox available on GitHub with a lot of open code where you can test and implement a bunch of fairness intervention mechanisms that have appeared out there. A shameless plug is that one of these methods is something that I developed while I was at IBM. It's something that looks like rate distortion theory, so I do encourage you to check that out. And to wrap up, with big data comes big responsibility, but I do believe that information theory can help. I feel like if you're looking for new problems, I think information theory can say a lot about privacy, fairness, and transparency of machine learning models. I've also found this as a great way for engaging with a new generation of students of getting interested in information theory. And if you want to learn more about some of the work that we've been developing in this direction, here are some references of some of our papers from the past couple of years. And just to wrap up, I want to thank my sponsors. This wouldn't be possible without the support of NSF, without the support of the Google Faculty Award and of IBM. Thanks.
Thank you, Flavio. So I have a quick question.
Sure.
Maybe it's a very high level, but a little bit technical. So, I mean, in terms of the fairness, what I understood is that you try to see how a perturbation on the distribution affects your fairness measure, or and then you try to perturb your distribution to make it more fair.
Yeah.
And that's kind of way of thinking, what does I guess what I didn't understand, what you call the counterfactual.
Yeah.
So is this the good distribution that you want to achieve, or it's?
Well, that would be the distribution that, given disparity metric, it would be the one that minimizes or almost or hopefully removes that disparity metric.
Okay, so this is the target. This is the good one.
Exactly, that would be the target one.
Okay.
Yeah. So, and again, by asking this question, we try to identify for example, features whose distribution you have to change more than others. Those are features that could potentially signal that those are proxies for a sensitive attribute, right? So, for example, if you're doing a recidivism prediction, predicting if someone will commit a crime again or not, and you know that criminal history is one of the features that you use, and that feature has a very different distribution across two different populations, that could be a potential proxy for discrimination.
Okay.
And we just try to systematically flag that.
Okay. So I don't know if there are other questions. Yeah, if not, so people can maybe watch it later on YouTube, the talk, or comment or ask questions later offline. Yeah. And I want to thank you again, Flavio, for the talk, and we'll see you soon, hopefully.
Yeah, thanks.
See you.